Alrighty, today, ladies and gentlemen, we are going to be looking at the fundamental counting principle and combinations. So the fundamental counting principle reads, let E1 and E2 be two different events. The first event, E1, can occur in M1 different ways. After E1 has occurred, E2 can also then occur in M2 different ways. The number of ways that the two events can occur is M1 times M2. So this is all a bunch of gibberish, but we're going to put some context in it in a second. And I want to say in this definition, it's only E1 and E2, but this can be extended to 3 or more events, and we're definitely going to see what that looks like. So our first question that we are going to look at is how many ways or how many different pairs of letters that we can make out of the English alphabet. So we have letters, and we know that there are 26. So I could just start listing. I got like A, B, A, C, A, D. Yeah, that's going to take forever. I'm not doing that. There's 26 letters, and then doing that for each letter, that's just crazy. I'm not ever going to do that. So we can use the fundamental counting principles to see, what's going to happen. So we could say E1 is our first letter, and then M1 is 26. So our first event, E1, can occur in M1 different ways. The first letter can have 26 different letters. We could do the same exact thing, copy, paste, because E2 can happen in M2 different ways. And then based off this fundamental counting principles, we have that this is equal to M1 times M2, is then equal to 26 times 26, or 676. So there are 676 ways that we can order 2 letters inside the English alphabet. Now let's move on to something slightly more advanced. We're going to use more than 2 terms this time. If you would like to follow along in the book, we are going to look at number 13. So this is 13 in the book on page 613, if you'd like to follow along, but I'm just going to narrate it. So it says a customer can choose one of 4 amplifiers. So I'm going to say A is 4. There's 4 amplifiers. There are 6 CD players. So I'm just going to write C is 6, and speakers are 5. There are 5 speaker models for an entertainment system. And then it asks, what's the possible number of configurations? So we can do the same thing that we did before. Our event 1 is going to be our amplifier. Event 2 will be our CDs. And event 3 is going to be our speakers. Now, M1 is the number of different amplifiers. So that is 4. M2 is our number of CDs, which is 6. And M3 is our number of speakers. That is 5. Just like we did right here. We then multiply M1, M2, M3. We get 4 times 6 times 5. This is equal to 120 ways. 120 ways. So basically what we're doing is we're multiplying how many different ways each event can be ordered or something like that. In a lot of these, there's going to be ordering or just how many combinations. So let us we'll do one more and then we'll move on. So this is going to be 17 in the book, and it reads, how many 3-digit numbers, so we're dealing with 3-digit numbers, can be formed under each condition, For A, we have our leading digit cannot be 0. So now we think about it. So our event 1 will be, let's actually think about what a 3-digit number looks like. So we have called digit 1, digit 2, and digit 3. I'm just going to underline it for these spots. So we have that digit 1 can't be 0. So how many digits can it be? How many digits can it be? It could be 1, 2, 3, 4, 5, 6, 7, 8, 9. So D1 is equal to 9. Now, D2 is then, and this is like what we're doing with our D1 and D2. This is like the same, oops, I erased, I meant to highlight. This is like the same thing we're doing up here with this M1 and M2. We're writing out how many combinations each space could be, or what each space has a possibility to be. D2 doesn't have any restrictions. Our second digit, our tens place, so it could be 0 through 9. That is 10 digits, and we get the same thing for the last space. Do the same thing, D1 times D2 times D3. That then will be equal to 10 times 10 times 9. That is equal to 900. And then let's just do B, and then we'll leave C for maybe class. Now this one is the same thing. Our leading digit can't be 0, and then there are no repeat digits. No repeat digits. So I'm going to copy our same little setup that we have. Bring that on down here. So our leading digit can't be 0. So that is going to be 9 again for D1. Now what can D2 be? So we know that D2 in this problem, in A, is 10, because it can also be 0. But it can't be a repeat of what D1 is. So whatever D1 is, D2 cannot be. So we have to subtract 1 from the possibilities. So D2 is also 9. We subtract 1 from the possibility of 10 digits because D1 would be that. For example, if I say our first digit is 3, then D2 can be 0, 1, 2, not 3, 4, 5, 6, 7, 8, 9, and that would give you this 9 possibilities. Now our last one, D3, you gotta think, so it can't be a repeat of D1, and it can't be a repeat of D2. So now we have to take off 2 from our total of 10. So we have 9, 9, and 8. We do our same thing. We can then multiply. That's going to get us 9 times 9 times 8. And that will equal 648 numbers. So this is what the fundamental counting principle is. It's basically you take the number, or you take an event, any event. So in this case, with our digits, our first digit is one event, our second digit is another event, third digit is another event, and each one of those can occur in a different ways, and this is going to change based off of conditions set in the problem. So for example, in 17a, our leading digit right here could not be 0, so that's going to change the amount of ways that this M1 here can occur. And then we just multiply those together like this, And if we have more than 2, which our definition doesn't exactly cover, you can still do that. You just multiply theoretically up until, infinity. If you have 10 different, you have M1, M2, M3, M4, M5 for all these different events, you can multiply all those together. So now that that's all said and done, we can move on to some more fun things. We've already talked about what this beautiful little formula is. This n choose r. We know this as the binomial coefficient. It is also able to be used to calculate the number of combinations of n elements taken r at a time. So that's where this n choose r comes from. If I have 10 things in a bucket and I want to know how many combinations I can pick up 2 different things, this is going to be the equation for me. So let us look at a handy dandy example. I have example number 62 in the book that we're going to look at using this. So it says, write all possible selections of 3 letters that can be formed from the letters A, B, C, D, E, and it does include F. A, B, C, D, E, F. So how many ways can, we calculate this? So we could sit there and list all these ways out. Kind of sounds like a pain in the butt to me, so we're not going to do that. Oh, one thing. This is very, 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 very mucho important. When we're talking about combinations, I'm actually going to move this down. And this is the biggest defining factor. Order does not matter. Order does not matter. Order does not matter. So if we look at, what one of our possibilities for 62 is for a 3, picking out 3 of these letters, we can have ABC. In combinations, ABC is going to be the same thing as BAC or CBA. They all count for the same thing because the order does not matter. When we talk about permutations, that sort of thing will matter. That order will matter. And that is going to be what we do on Friday. We're going to do permutations on Friday. But that's a whole nother ballpark that we're not going to get into today. So, 62. Write all possible selections of 3 letters that can be formed from these letters, A, B, C, D, E, F. So we basically just fill out, we have 6 letters, and we are choosing 3. So that will be equal to 6 factorial over 6 minus 3 factorial times 3 factorial. This then is equal to 6 times 4 times, I skipped 5. 5 times 4 times 3 factorial over 3 factorial. We can some handy dandy canceling. And then we do know that 3 factorial is 3 times 2 times 1, or 6. Do some more canceling. The 6's are going to cancel out, and we are left with 20 ways. We're left with 20 ways. Now, we're going to move into something a little bit more interesting to me. So we're going to move into something called game theory. Do a question on game theory and calculating how many different possibilities there are to come up with this, combination of cards if we're playing a game like poker or something like that. Texas Hold'em. I actually don't really know any card games, if we're being honest. I played poker like 3 times in my life. So, with that aside, 69 has 5 cards are chosen from a standard deck of 52 cards. How many 5-card combinations contains 2 jacks and 3 aces? So 2 jacks and 3 aces. This is gonna combine, what we've been talking about with this combinations, and then also our fundamental counting principle. It's gonna kind of slam all of it into one. So let's think about ways to select 2 jacks. So there are a set of 4 jacks inside of a deck of cards. So we have 4 jacks, and we are choosing 2 of them. So let's look at our formula again. We have 4 factorial over 4 minus 2 factorial, 2 factorial. 4 factorial is 4 times 3 times 2 times 1. 2 factorial is 2 times 1. Then we have another 2 factorial. So this all cancels out. And 2 factorial is just 2. I'm just going to write it out so that everyone understands what's going on. So we have 12 over 2, or 6. So this is 6 ways to select 2 jacks, where the order does not matter. And we're going to do the same thing with our 3 aces. We're going to do 4, choose 3. So we have 4 factorial over 4 minus 3 factorial and 3 factorial. If you notice, 4 minus 3 is just 1 factorial, which is 1, but I'll just write that in anyway. 4 factorial can be written as 4 times 3 factorial. Cross those out, and all we are left with is a nice 4. There's an S here. Ways to select 3 aces. Now, so we have our 2 different events. We could say E1 is our jacks, and E2 is our aces. So the different ways is going to be M1 is going to equal 6. M2 is going to equal 4. And this then is going back up to this counting principle. Our first event, selecting or our jacks, can occur in how many different ways? We calculated that. That's 6. Our second event, our aces can go in M2 different ways. And we found that to be 4. So now what do? Do what we've done before. M1 times M2 is equal to 6 times 4 equal to 24. Very good. All is good and well. So these questions kind of require some outside of the box thinking, especially on how to set these up. If you notice, if you read this straight from the book, you're going to have some information that you don't even really need, like the fact that there's 52 cards in the deck. That doesn't once appear. We're already assuming, that we have these combinations of jacks and aces in our hand. So it's going to take a little bit of context, a little bit of reading, and a little bit of thinking to be able to get good at these problems. But I believe that all of you can do it. So, talk about fundamental counting principle and combinations. So I hope you guys had a wonderful day and a good rest of your day. With that being said, we will see you hopefully in the next video if you decide to do your homework. Have a good one.